Hi, my name is Michael Rosenberg. Today I'm going to be presenting SNARKBlock, which is a scalable anonymous block listing scheme. This is joint work with Mary Maller and Ian Miers. So first we start off with motivation. It's important to maintain multiple identities on the internet. For example, you might not want to use the same identity in an online setting, in a church group, and a queer social group. To this end, anonymous or pseudonymous speech is immensely useful. The problem is, to block abusive users, you need some form of banning, and to make sure they don't come back, you need to know who they are. Unfortunately, service providers are increasingly solving this banning problem by tying every user to a strong identity, whether it's through phone number, IP address, or photo ID. In fact, this seems like an inherent trade-off. You can have anonymity or accountability, but you can't have both, it seems. So our research question was, how do we block trolls, prevent sock puppets, and allow anonymous posts? Surprisingly, cryptography provides a solution here that maintains privacy. So let's look at that now. So we start off with the anonymous block listing scheme due to Tseng et al. From 2007. So we have Alice, who's a user, and Daily Science Fiction, which is a service provider. Further, we suppose that Alice has terrible taste in sci-fi. In fact, her taste is so garbage that she's embarrassed about the comments that she makes on the website, and she would like to remain anonymous. Furthermore, Daily Science Fiction reserves the right to ban users for any reason at all. So to combine this notion of anonymity with banning, we introduce a block list, which contains pseudo-random tags. These tags are associated with every single comment that is posted on the website, but they're not linkable to the person who posted them. So in the process of sending a message, Alice will send her own tag associated with that message, which again is pseudo-random, and also a proof. The proof says, essentially, here is a random-looking token in case you want to ban me in the future. You just put that on your block list. And the tag and the proof is that none of Alice's tags already exist on the block list. In other words, Alice is not banned. There's some problems with the existing work, which is also the state of the art in the field. First of all, and the main one, is for 4 million bans, the proof size is over half a gigabyte. So if we just estimate the upload time on a 50 megabit per second system, which is 5 times the median in America, that is over 1.5 minutes just to verify, not even including computation time. And the second issue is that proof reuse is not allowed by the system, so Alice has to make her proofs from scratch every single time she posts a comment. So our contributions are twofold. We have a system, SNARKBlock, that's built on a primitive HiChop. HiChop is a zero-knowledge proof scheme that itself aggregates other zero-knowledge proofs. HiChop has some properties that we use in the construction of SNARKBlock. One property is update unlinkability, so the underlying proofs, the list of underlying proofs can be appended to, and we don't have to modify all of them we don't have to recompute all of the underlying proofs every single time. We could just add to the list, and then we get a new HiChop proof. And so we use that for work reuse in our block listing scheme. The second property is that HiChop proofs are succinct. In particular, they're logarithmic in the size of the number of proofs that they aggregate. And what that means for us is that we get scalability in our block listing scheme because our proofs become logarithmic in the size of the block list itself. So concretely, SNARKBlock has proof sizes for 134 million bans. We'll have a proof size of 200 kilobytes, and this takes less than a second to upload and verify for the server. So we believe that this is closer to what is considered scalable. So we'll start with the existing block listing scheme from Black, and we're going to see what goes wrong with it, and then we're going to iteratively fix it until we arrive to SNARKBlock. So let's see what happens when Alice tries to log in when the block list is empty. First, we note that she has an identity. This identity is a random number, essentially, that is only known to her. This is tied to her as a person and not known to daily science fiction. Alice will sample a nonce that's random, and she will compute a tag, which is a pseudo-random value, or it's a pseudo-random function evaluated on the nonce. Again, this tag is pseudo-random, so it's unlinkable. And she will compute a proof that says basically that the tag is well-formed, i.e. that the tag is the result of the PRF on the nonce. She'll send the nonce, the tag, and the proof to daily science fiction, and daily science fiction will verify if it's all good. Now what happens when Alice logs in when there is a block list? She'll sample a nonce just as before. She'll sample a tag, and she'll compute the tag as a PRF again. And she'll also compute the proof just as before that the tag is well-formed. And in addition, she will add a bunch of terms to the proof, basically saying my tag, none of my previously computed tags appear in the current block list. And so she's going to have as many terms as there are on the block list. And then she's going to send the nonce, the tag, and the proof just like before, and daily science fiction will verify. So this is Black's scheme. And the main problem is that the proof is not succinct, right? The proof size, as I mentioned, it grows with the number of terms in the bottom of this box, which is the size of the block list. So a linear size proof means that verification time is also linear, which means that this doesn't scale. So our primary goal here is to allow for sublinear proof size and sublinear verification time. So first question, why can't we just make this a snark? Right, a snark is a zero-knowledge proof of knowledge that is succinct. And succinctness basically means, at least in the ones that we were looking at, that the proofs are constant size and verification is constant time. So if you just do that, now your verification is constant time and you're done, right? Well, the main problem is that this is really slow. For a proof, for 2 million terms, this is going to take 3 hours on a 256 core cluster. That's unreasonable. Also, for trusted setup circuits, the circuit size will have to increase every single time you increase the block list, and you're going to have to do a setup every time. So let's try to fix this. We like the idea of snarks, but it grows too big. So why not just break this up into many smaller snarks, right? So take the block list, chunk it up into chunks of, say, size 10, right? You have S many chunks. And you're going to compute the well-formedness proof like before. The tag is the result of the PRF. And you're also going to compute a proof for every single chunk saying that, that none of my tags that I've ever computed appear in chunk 1. None of my tags that I've ever computed appear in chunk 2, etc. And then you basically send the nonce, the tag well-formedness proof, and then all of the chunk proofs. So the first problem with this is that we're back to linear again, right? If the chunk size is fixed, then the number of proofs is linear, so this doesn't scale again. And the other issue is that this actually has a consistency problem. There's nothing that shows that the identity in all of these proofs is the same. In fact, Alice could have used one identity in one proof and another identity in another proof, and she could have evaded a ban by using the identity that was not banned in that particular chunk. So let's try to fix the second problem here, the ban evasion one. You can do a commit and prove scheme where you compute a commitment to the identity and then make all of these proofs with respect to the commitment. Now this commitment is hiding, so it doesn't reveal anything, and you can show that all of these are made with respect to the same identity. So then you would just send the commitment along. Why doesn't this work? Well, you can do this, but then you can't reuse any of the proofs because the proofs are now made with respect to this fixed commitment. And if you have to send that commitment again, you're linking yourself across different attestations. So what we need is a hidden common input aggregate proof, right? We have to show that these hidden inputs, i.e. the identity, are consistent across the proofs, right? And at the same time, we need it to be succinct. So this is exactly the property that HiChop provides. It is succinct. It has update on linkability so that you can incrementally increase the number of proofs underlyingly. And it shows that all of these proofs have a consistent input. So the way this works is you have all of your chunk proofs, you aggregate them together, and you produce a single aggregate proof that also internally links all of these identities together without revealing externally what those identities are, unlike in the commit and proof scheme. And so then the only thing that you're sending is the nonce, the tag, and the logarithmic-sized aggregate proof. So our scheme SNARKBlock, simplified, goes as follows. We now have a block list, which is a sequence of chunks instead of a sequence of just nonce tag pairs. And Alice has a bunch of her chunk proofs pre-computed. She can do these offline. She will sample her nonce, compute her tag like before, and compute her tag well-forwardness proof, and then compute an aggregate proof over all of the chunk proofs and the tag well-forwardness proof. This is using HiChop. Then she'll send her aggregate. Daily Science Fiction will verify. So let's look at performance. So first we look at verification costs, since this was the motivation initially. Scalability is determined by how many users a server can handle. So verification is what the server is going to be doing for the most part. So for chunk size 8192, at the block list size 134 million elements, the aggregate proof is going to be 200 kilobytes, and the verification latency is going to be less than 230 milliseconds. And we have graphs here showing the logarithmic behavior, the logarithmic proof size and throughput behavior of the verification routines and the proof sizes. Comparing this to Black, for just 4 million elements, the proof size is over ½ gigabyte, and the verification latency, we upper bound by just the upload time, because it's certainly larger than the upload time, and the upload time itself is 1.5 minutes. So now we look at proof costs. So recall Alice has to recompute a new chunk every time a batch of additions is made to the block list. So we estimate the offline chunk proof time, or we benchmark the offline chunk proof time is about 200 seconds for every 12,000 bands. And we also have end-to-end benchmarks, which show that, again, for 134 million, a small chunk recomputation plus a full attestation, including the aggregation, plus upload, plus verification cost is going to be 23 seconds. We note that we get all the security properties you would want out of this scheme. Blocklistability says that if you're blocked, you're actually blocked. You can't log in. Non-frameability says that no one but the server could force you to be effectively blocked. And anonymity means that you are anonymous. So in summary, we asked how do you get block listing that scales to millions of users, and we provided HiChop, which is a SNARK aggregation scheme with update on linkability, and we used HiChop to construct SNARKBlock, which has less than 1 second verification time for 134 million bands. Proofs are fast too. These are the properties, and that's my time. Questions?
Yeah, so I was wondering if you have to re-download the entire block list as a client, or can you just download the delta of the new edition?
Yeah, you can do deltas.
Okay.
You can just download whatever changed in between attestations.
I see. Thanks.
Great work, thank you. Have you considered using an accumulator to prove that a tag nonce tuple is not part of the block list, or what will be the trade-offs here?
Right, so we actually did look at accumulator-based schemes. So one of the issues we had with that was, I think they were mostly used in de-anonymizing schemes. They required a de-anonymizing party that you trusted in order to add someone to the accumulated value. So that's why we couldn't make that work.
Thank you.
We have time for a few more questions. Okay, I have a question. So what do you envision that we can use for these tokens or identities, and how do we make them hard to obtain?
Right. So this is this notion is basically how do you get strong Sybil-resistant identities on the internet, right? So currently, what people do is they will rely on your real name, or they will ask for your passport, or they will ask for your phone number, right? Facebook or Gmail, for example, ask for your phone number. So obviously this isn't ideal, but currently it is one of the most widely used Sybil resistance mechanisms. So you can imagine an identity provider would use that or use whatever existing mechanisms exist in order to issue identities. And so the main benefit here is not that it is a new Sybil resistance mechanism, but rather it just separates the identity provider from whatever that user ends up doing. We have actual separation between who someone is, or rather the fact that a person is human, and then whatever they end up doing on the internet.
Makes sense. Thanks.
Hello, great talk. Saurabh from UIC. So I was wondering, why do you get logarithmic? I think you use Groth16 everywhere. So where does the logarithmic shows up?
Yeah. So the aggregation technique is due to the paper name is proofs on inner pairing products or something like that. It's in the paper, but basically the Groth16 verification equation is really simple, right? It's a single equation, and it looks like and if you have a lot of them, you can basically turn it into an inner product, where the inner product operation is a bilinear pairing. But now that you have something that uses inner products, you can do standard folding methods. So if you're familiar with the sum check technique, you can basically just fold in logarithmically many steps.
Okay, thanks.